Neuromorphic computing with ionic liquids is an emerging approach that aims to mimic the brain's architecture and dynamics by leveraging fluid-based materials. This method uses ionic liquids, salts in a liquid state at room temperature, as active components in computing systems, enabling them to process information similarly to biological neurons and synapses. How can a liquid contribute to computing? The key lies in the unique properties of ionic liquids, such as high ionic conductivity and tunable electrochemical behavior, which allow them to function as dynamic, reconfigurable elements in neuromorphic circuits. In these systems, ionic liquids can be incorporated into devices like Memristors, components that remember the amount of charge that has flowed through them, mimicking the way synapses in the brain strengthen or weaken over time. For example, by adjusting the voltage across a Memristor containing an ionic liquid, researchers can control the movement of ions, which in turn alters the device's resistance in a way analogous to synaptic plasticity. This capability is crucial for developing AI systems that learn and adapt in real time. How does this compare to traditional silicon-based hardware? Traditional processors execute pre-programmed instructions, whereas neuromorphic systems using ionic liquids can process and store information simultaneously, leading to potentially lower energy consumption and faster learning capabilities. Another exciting aspect is the reconfigurability offered by ionic liquids. Their fluid nature means that the arrangement of ions and thus the behavior of the device can be dynamically adjusted, allowing for the creation of circuits that change their connectivity in response to external stimuli. This adaptability mirrors the brain's ability to rewire itself in response to new information or experiences. Researchers are exploring how this dynamic reconfiguration could be harnessed to develop AI systems that are not only more efficient, but also more robust against disruptions. Could such fluid-based computing revolutionize how we design AI? The potential is there. Systems that mimic the brain's efficiency could lead to breakthroughs in areas like pattern recognition, decision-making, and autonomous control. Practical applications of neuromorphic computing with ionic liquids include the development of smart sensors, adaptive robotics, and energy-efficient data processing systems. Imagine a robotics system that can adjust its neural network on the fly to better navigate unpredictable environments, or a sensor array that learns from its surroundings and optimizes its responses without needing constant external updates. These examples highlight the promise of combining ionic liquids with neuromorphic architectures to create computing systems that are both flexible and highly efficient. By integrating ionic liquids into neuromorphic designs, scientists are paving the way for next-generation AI hardware that leverages the dynamic, adaptive properties of fluids. This research is still in its early stages, but initial experiments and prototypes are already demonstrating exciting capabilities. How might these innovations impact the future of AI? With ongoing advancements, neuromorphic systems based on ionic liquids could lead to AI that learns faster, operates with lower power consumption, and adapts more robustly to new tasks, qualities that are essential for the next wave of intelligent technology. Neuromorphic computing mimics the structure and function of the human brain to process information more efficiently than traditional computers. Ionic liquids are room-temperature molten salts with unique conductive and adaptive properties that can serve as the medium for fluid-based computing. Integrating ionic liquids into neuromorphic architectures enables dynamic and reconfigurable circuits that better emulate neural networks. This emerging field aims to develop AI systems that operate with low energy consumption and high parallelism. A research prototype might use an ionic liquid-based circuit to simulate synaptic activity, achieving rapid, brain-like signal processing. It's like replacing rigid circuit boards with a flexible flowing gel that can rearrange itself to form new connections. Similar to how neurons rewire in the brain, ionic liquids exhibit high ionic conductivity, low volatility, and excellent thermal stability, making them ideal for electronic applications. Their fluid nature allows for the self-assembly of conductive pathways that can change dynamically in response to electrical stimuli. These characteristics enable the development of computing systems that are adaptive and reconfigurable. Their unique properties are harnessed to create circuits that mimic biological processes at the nanoscale. A lab demonstration may show an ionic liquid forming temporary conductive bridges between electrodes when a voltage is applied, thereby altering the circuit configuration in real time. It's like using a thick conductive syrup that can flow and reorganize itself to create or break connections, much like water forming puddles and streams in response to gravity and obstacles. Neuromorphic architectures aim to emulate the parallel processing and adaptive learning capabilities of the human brain. Fluid-based circuits using ionic liquids can dynamically change their structure, enabling real-time reconfiguration similar to synaptic plasticity in biological systems. This architecture supports nonlinear processing and efficient pattern recognition, essential for advanced AI applications. By leveraging fluid dynamics, these systems offer a promising path to overcome limitations of conventional silicon-based circuits. In a prototype neuromorphic chip, ionic liquid channels rearrange themselves to optimize signal pathways based on input data, mirroring how brain synapses strengthen or weaken over time. It's like a city's road network that can be rerouted on the fly to reduce traffic congestion. Paths are optimized dynamically based on energy efficiency is a key goal in developing next-generation computing systems, and neuromorphic devices aim to significantly reduce power consumption. The use of ionic liquids allows for low energy switching and reconfiguration due to minimal physical movement and low resistance pathways. These systems operate on principles similar to biological neurons, which perform complex tasks at very low energy costs. The synergy between ionic liquids and neuromorphic design offers promising improvements in sustainable computing performance. A fluid-based neuromorphic circuit may operate with orders of magnitude less energy than traditional microprocessors when performing complex pattern recognition tasks. It's like comparing a fuel-efficient electric car that uses minimal energy to drive long distances with a traditional gas-powered car that consumes much more fuel. Self-assembly in ionic liquid-based systems refers to the ability of molecules to organize spontaneously into functional structures under appropriate conditions. This phenomenon allows circuits to reconfigure themselves, creating new pathways for information processing without manual intervention. Such reconfigurability is analogous to the brain's ability to form new synaptic connections in response to learning and experience. The dynamic nature of these circuits is central to developing adaptive, flexible AI systems. In experimental setups, ionic liquids can form and break conductive paths in response to external signals, effectively rewiring the circuit for optimized performance. It's like having a set of Lego blocks that automatically rearrange themselves to build a better structure when new challenges arise. In neuromorphic computing, memory and processing functions are integrated, mimicking the way biological neurons store and process information simultaneously. Ionic liquid circuits can serve as dynamic memory elements that change state in response to electrical inputs, effectively encoding information. This capability allows for real-time learning and adaptation in AI systems. The fluid nature of these materials supports continuous reversible changes that underpin efficient memory storage. A neuromorphic system might use the state of an ionic liquid-based synapse to store information, with the state altering as the system learns from new data inputs. It's like a chalkboard that can be erased and rewritten repeatedly, allowing new information to be recorded while maintaining a connection to previous notes. The adaptive and dynamic nature of ionic liquid-based neuromorphic systems makes them well-suited for integration with advanced AI algorithms. These systems can perform complex computations and learning tasks more naturally and efficiently than traditional hardware. They support parallel processing and real-time decision-making, essential for applications such as pattern recognition and autonomous control. Integrating these technologies promises to enhance the performance and efficiency of AI systems significantly. An AI-driven robotic system may utilize a neuromorphic chip with ionic liquid circuits to process sensory data in real time and adapt its behavior dynamically. It's like having a personal assistant who not only processes information quickly, but also adapts to your needs on the fly, learning from each interaction. Despite their promise, integrating ionic liquids into neuromorphic computing faces challenges such as ensuring long-term stability and scalability of the fluid-based circuits. Maintaining consistent performance over time requires overcoming issues related to material degradation and environmental sensitivity. Researchers must develop methods to control the fluid dynamics precisely and integrate these systems with existing solid-state technologies. Addressing these challenges is critical for transitioning laboratory prototypes into practical commercial devices. Prototype devices may perform well under controlled conditions but need further refinement to ensure reliability when exposed to varying temperatures and humidity levels in real-world applications. It's like designing a high-performance sports car that works perfectly on a test track but needs additional engineering to handle everyday roads and weather conditions reliably. Future research in neuromorphic computing with ionic liquids aims to further integrate fluid-based systems with advanced computational frameworks, expanding their application in various fields. This interdisciplinary area merges principles from quantum physics, materials science, chemistry, and computer engineering to push the boundaries of what is possible. Advances in this field could lead to AI systems that are not only energy efficient, but also capable of real-time adaptation and learning. Continued innovation in this space promises to revolutionize technology, with far-reaching implications for computing, robotics, and beyond. Future devices may combine ionic liquid circuits with machine learning algorithms to create self-optimizing sensors for environmental monitoring, significantly enhancing their responsiveness and efficiency. It's like evolving from a basic smartphone to a smart assistant that learns from its environment and adapts its features to suit your needs, creating a seamless and dynamic user experience.